Good morning to all. Welcome back to the course PH8253 Physics for Electronics Engineering. We are discussing Unit 3 Magnetic and Dielectric Properties of Materials. In the previous class, we arrived at an expression for polarization. In today's class, we will be discussing the various types of polarization. The types of polarization include electronic polarization, ionic polarization, orientational polarization, and space charge polarization. So the electronic polarization is denoted as Pe, ionic polarization as Pi, orientational as Po, and space charge as Pm. The space charge is sometimes called migrational polarization or interfacial polarization. It is a characteristic of heterogeneous dielectric media. Its contribution is very less in case of homogeneous dielectric media. The net polarization P is the sum of electronic polarization, ionic polarization, and orientational polarization. If N is the total number of atoms or dipoles within unit volume of the given material, then electronic polarization Pe is given as N alpha E times the applied electric field E. Similarly, Pi is N alpha I times the applied electric field, and Po is N alpha O, the applied electric field. As I told earlier, N denotes the number of atoms per unit volume and E is the applied electric field. The quantities alpha E, alpha I, and alpha naught are polarizabilities. The sum of the electronic polarizability, ionic polarizability, and orientational polarizability is the net polarizability alpha. Alpha equal to alpha E plus alpha I plus alpha naught. The dipole moment induced is proportional to the applied electric field E. The proportionality constant is called the polarizability alpha. With this background, let us discuss about electronic polarization. It is observed in atoms that are polar. When you have a nucleus with a charge Ze surrounded by an electron cloud of charge minus Ze, and if the applied field is 0, then the net polarization is also 0. This can be visualized as both the nucleus as well as the electron cloud having the same center of mass, which means x equal to 0. Suppose there is an applied field in this direction, then The electron cloud gets displaced by an amount x from the previous position. So the induced dipole moment in this atom is now Zex, where Z is the charge and X is the separation between the charges. In order to find X, let us equate the Lorentz force minus ZE. Let us equate the Lorentz force minus ZE and the Coulomb force. Coulomb force is given as ZE into the charge density times the volume x 4 by 3 pi x cube by the distance square 4 pi epsilon naught x square. Here the charge density rho is given as minus ZE by 4 by 3 pi r cube, where r is the radius of the atom. So substituting the given values and on simplifying, we get electric field E equal to ZEX by 4 pi epsilon naught r cube. Or in other words, the dipole moment mu is ZEX, which is equal to 4 pi epsilon naught r cube E. From the definition of the dipole moment, mu equal to alpha EE, we have alpha E, that is the electronic polarizability, equal to 4 pi epsilon naught r cube. We can infer that the electronic polarizability is independent of temperature, whereas it depends on the atomic size r. So this is one expression that we have arrived at from the discussion of electronic polarization. Now let us discuss ionic polarization. As the name suggests, ionic polarization occurs in ionic molecules. Let us consider the Na plus and Cl minus ion, that is sodium chloride ion. In the absence of external field, both ions are at a distance d by 2 from the center of mass. Hence, the dipole moment is zero. But when an electric field E is applied, they get displaced from the center of mass by different amounts, and let Na plus be displaced by an amount x1, whereas Cl minus is displaced by an amount x2. Small m is the mass of Na plus and capital M is the mass of Cl minus. Then the Lorentz force EE is given as m omega naught square x1 for Na plus ion, whereas it is m omega naught square x2 for Cl minus ion. The dipole moment in this case is E times X. X being the sum of x1 and x2. Comparing these two equations, you have x1 plus x2 to be equal to E by omega naught square 1 by m plus 1 by m. On substituting, we have the induced dipole moment to be E square by omega naught square into 1 by m plus 1 by m E. So on recalling that the induced dipole moment is proportional to electric field, with proportionality constant being the polarizability, the ionic polarizability alpha I equal to E square by omega naught square into 1 by m plus 1 by m. As you can see, this quantity is called the reduced mass of the molecule. So the ionic polarizability depends on the reduced mass. Ionic polarizability is also independent of temperature. Now let us discuss about orientational polarization. In a polar dielectric, in the absence of external field, the electric dipoles are randomly oriented. But when the field is applied, when an external field is applied, the dipoles get oriented in the direction of the applied field. Here, mu is the electric dipole moment. You have a charge plus q and minus q separated by a distance 2L, separated by a distance 2L, then q into 2L is the dipole moment. The orientational polarizability is given as mu square by 3 kT, which is from Langmuir's theory. The orientational polarization is given as n alpha naught. Alpha naught is orientational polarizability. Unlike the electronic and ionic polarizability, orientational polarizability depends on temperature. It occurs only in polar dielectrics. It is inversely proportional to temperature and it is directly proportional to the square of the dipole moment. Space charge polarization, as I said earlier, occurs in case of heterogeneous dielectrics. It is also temperature dependent. It is the accumulation of charges near the electrodes. So if the space near the electrodes gets electrified or gets charged due to the high field, space near the capacitor plates is getting charged, then that is called space charge polarization. In case of dielectrics that are homogeneous, the contribution due to space charge polarization is negligible. Hence, the total polarization P is usually the sum of electronic polarization, ionic polarization, and orientational polarization. And the polarizability alpha is the sum of alpha E, alpha I, and alpha naught. When we substitute for these values, we have 4 pi r cube, 4 pi epsilon naught r cube plus E square by omega naught square 1 by m plus m 1 by m plus mu square by 3k. Substituting these values, we have P equal to n alpha E, which is n times 4 pi epsilon naught r cube plus E square by omega naught square, where omega naught is the natural frequency of the oscillator, 1 by m plus 1 by m plus mu square by 3kt. This expression for polarization is called as the Langevin-Debye equation. So in today's class, we have discussed about 4 different types of polarization and arrived at expressions for polarizabilities and the net polarization. Thank you for now.